let's open a notebook and let's start to learn how to code a digit classifier based on image processing and neural networks. This will be done in 4 steps. First, we'll load and visualize the dataset. Second, we will define the model architecture. Third, we will train the model. And fourth, we will use the trained convolutional neural network to recognize digits in new images, or in other words, to make predictions. Let's start by uploading the library NumPy and the file helperfunctions.py. For this latter, we need to click on Files on the left tab, select Upload, and pick the file from your disk. The function contained in helper function will help us read, visualize, and store the images from our dataset in matrix form. The dataset we will use is the open source MNIST dataset, which contains 28 by 28 pixels grayscale images of handwritten digits from 0 to 9. Each example in the dataset contains an image and its label indicating which digit it represents. We will use 2 separate datasets, one for training the network called training dataset, and one for evaluating its performance called validation dataset. We need to upload the file digitdataset.zip containing the MNIST dataset in the Colab folder. And to do so, we click Files on the left tab, select Upload, and pick the zip file from your disk. Once done, we extract it with the unzip command by running this cell. And to load the training dataset, we need to specify the path to the folder containing the images and their labels. We then use the load data function, defined in the helper function files, to store the matrix representation of images in Xtrain and the corresponding labels in Ytrain. So let's explore our dataset using the function showRandomSamples, which is defined in helper function. And this function randomly picks 4 images from the dataset we just loaded and shows them. The parameter baseDir specifies the path from which we are picking the images, while setting digit equal to 5 tells the function to display 4 randomly selected images of the digit 5. It's convenient to first set the random seed for reproducibility, and this forces the random number generator to produce a fixed sequence of numbers each time the code is run. So here are 4 examples of the digit 5. Next, we prepare the validation dataset by calling the same loading function. But this time we use a different path. digitdataset/validationSet is the folder containing additional images that will not be used during training. Using again load data, we store the images in X validation and their labels in Y validation. Let's see how many images are contained in both datasets. Using the len function on Xtrain and X validation, we can see how many samples each dataset contains. Instead, to check the size of a single image, we use the shape property on the first element of Xtrain, which is the first image. And we can see that the training dataset contains 9,990 images, each made of 28 by 28 pixels, while the validation dataset contains 1,000 images. Now let's address the second step, the definition of the architecture of our classifier. In particular, we will use Keras based on the library TensorFlow to define an architecture that contains the main components of a convolutional neural network. We start by loading the libraries that we will need to define and train the network: TensorFlow, the interface Keras, and in particular, layers to easily define the network layers. For reproducibility of the initialization and training procedure, we use the command random set seed to fix the random seed used by TensorFlow. Now we can proceed to build our convolutional neural network architecture. To do this, we use Keras sequential to build a model as a plain sequence of layers. And first, Keras input is used to define the shape of the input image, which in this case is made of 28 by 28 pixels times one color channel. And the following convolutional neural network layers are provided by layered modules through specific classes. Com2D for the convolutional layer, max pooling 2D for the pooling layer, flatten for the flatten layer, and finally dense for the dense layer, which completes the classification task. And it's important to note that the inputs to these layers are design choices that depend on the problem, and they're usually fine-tuned through trial and error. And in this example, we will show you one specific configuration, but we encourage you to try different ones and see how results change. So let's see in detail how to define these layers, starting from the convolutional one. The first argument to Com2D layer is 32 and sets the number of filters. And the second one, 3,3, is the size of each filter, making each filter a small 3x3 matrix with learnable entries. We then set the activation function to ReLU to keep the output positive. And the padding option, same, ensures that the output has the same size as the input. So as a result, the output of the convolutional layers are 32, 28 by 28 matrices. And it's worth noting that since each filter has 9 learnable coefficients, we have so far 9 times 32 parameters to be optimized. But we will come back to this later. Next, we apply max pooling. And in the argument, we define the pool size, which in this case is 7 by 7. This means that this layer chooses the max within each 7 by 7 window. This reduces the dimensionality significantly, so 28 by 28 matrices are reduced to a size 4 by 4. At this point, we convert the set of matrices into a vector format that the dense neural network can receive as input. And this transformation is done by the flatten layer. And note that this layer does not perform any computation on the data. It simply reshapes it, transforming the set of 32 matrices into a 1D vector with 512 elements. The dense layer is then the final layer in our convolutional neural network architecture. The first argument, 10, defines the number of outputs corresponding to the 10 possible classes in our classification task that are the digits from 0 to 9. The second argument is the softmax activation function. And we have now finished defining our convolutional neural network architecture. But remember, along our way, we have seen many unknown parameters that need to be found. They are the filter's entries and the weights and biases of the dense layer. And this is the task for the training process, which, remember, is an optimization problem in which we try to minimize the loss function. And to do it, first, we choose an optimizer provided by Keras. And in this case, we choose the stochastic gradient descent method, abbreviated as SGD, with an arbitrary learning rate here set to 0.01. Next, we call the method compile on our model. And this step prepares the convolutional neural network for training by specifying 3 input arguments: the optimizer, the loss function, and a performance metric. Since this is a multi-class classification problem, as a loss function, we use the categorical cross-entropy, and this quantifies how far the network predictions are from the true labels. The string accuracy tells the neural network to report the number of correctly classified images, both in the training and in the validation dataset. And finally, by calling the summary method, we can see that this architecture has more than 5,000 learnable parameters. And now we are ready to start the training process. We use an approach based on mini batches, meaning that at each optimization step, the network only processes a small subset of the dataset called a batch. And once the optimizer has seen the whole dataset, we say that the training epoch is completed. And in our case, we set the number of epochs to 20 and the batch size to 16, meaning that the model will update its learnable coefficient by processing 16 examples at a time. We also use the tracking function to monitor how the CNN performance evolved during training. And the fit function finally starts the training process. Its arguments are the training data that consists in images in XTrain and labels in YTrain, the maximum number of epochs for the optimizer, the batch size, the validation data, again containing images in X validations and label in Y validation, the tracker, and the flag that limits the amount of printed information. And here is the output of the code. At each epoch, the code displays the loss value both on the training and validation dataset and the accuracy metric. And by the final iteration, we can see that the model reaches a very satisfactory performance, an accuracy of about 94% on both datasets. So we are now at the fourth step. Let's look at some results using the function visualize digit prediction from the file helper functions. And this function visualizes from the validation set one randomly selected image, in this case of the digit 3, and displays the prediction probabilities made by the network. And for this sample, the model correctly classified the image as a 3 with a 99% confidence. So let's try another one, this time with the digit 5. For this other example, the model correctly classified the image as a 5, but only with a 57% confidence. And interestingly, it also assigned a 37% probability to the digit 3, indicating that there is some uncertainty or confusion between the two classes. And in this case, as a human, I would be confused too.